Okay, so the recording has started. Now I will share my screen. I hope my screen is visible. So hello everyone. This is NPTEL CS52 Spring 2024 Reinforcement Learning course by Professor Balaraman Ravindran of Computer Science Department in IIT Madras. And this is the week 10. Actually, this was supposed to be on 2nd April, Tuesday, but like due to some unavoidable circumstances, it's happening on Sunday evening. So let's begin with the session. I'm Sandarbh from Computer Science Department in IIT Bombay. So as usual, these are the details of the sessions. Like from next session, like it will be on Tuesday on the same link, and anyone who has taken this course can attend. So again, discussion will on practice assignments, problem solving, and doubt clarification. And the main aim is to like ensure two-way communication. So again, the expectation as usual is that you should have watched weekly lecture videos like of week 10 corresponding to this week and at least made an honest attempt on solving the weekly assignments and practice assignments. And as usual, it's recommended to read the certain and Barto book. But now, like since we are following a topic like which is not in this book, so maybe like you can read papers. Like I have linked those papers in the reading section. Also, as usual, slides and recordings will be made available to you later in the same spreadsheet. Okay, so as usual, like we will go in the following order. Practice assignment first, then problem solving. Again, this problem solving will comprise of questions which are not part of practice assignment or assignment. Then we will have demo, like today's demo will be on policy gradient and also on active critic. And lastly, we will move to the assignment. So these are the like big 10 topics. So first, like we started with hierarchical reinforcement learning. Like most of these topics were theoretical, and then we discussed types of optimality like hierarchical optimality, recursive optimality, and flat optimality. Then we moved to semi-Markov decision processes, SMDP. And then we like kind of discussed that there are three major frameworks of hierarchical reinforcement learning. First of them was options. Then we discussed options in detail and saw like how to learn with options. Second framework for hierarchical reinforcement learning is these HAMS. And third is like MaxQ, like which will be introduced in week 11. So these three are the popular ones. So again, like let's begin with the practice assignment then. So first question says that given a problem with well-defined hierarchy, what ordering would you expect on the total expected reward? For an hierarchical optimal policy, this is denoted by H, recursively optimal policy denoted by R, and flat optimal policy denoted by F. So we know that like flat optimal policy is the richest of them. Like you can represent it like this. Suppose this is the set of recursively optimal policies, then you can have the set of hierarchical optimal policies, and then finally you can have the set of flat optimal policy. So generally, like you would expect that the, the total reward, total expected reward given by a flat optimal policy will be at least more than at least like the reward given by this hierarchical optimal policy can be equal. Like sometimes what happens, this flat optimal policy and hierarchical optimal policy are same, and in same way like this relation holds here also. So the correct option will be this one, options. So R is less than equals to H less than equals to F. Like these characters denote the total expected reward corresponding to these three policies. Okay, then I'll move to the second question. So second question says that do flat optimal solutions give the solution do flat optimal solutions give the solution with highest expected returns? It should have been policy. Okay, either way. So give the solution with highest expected returns. Yeah, like we saw in previous question only, like they generally do, like the reward which is given by this flight optimal policy was the highest, right? So we have seen like this relation already. So according to this, this reward will be highest for this one, flight optimal policy. Okay, then I'll move to the next question. So the next question is this one. Which of the following are true for HAMS? So this is corresponding to hierarchical abstract machines. So again, like this is a multi-option correct. So the first option says that finite state machines in a ham must be connected in a directed acyclic graph. Yeah, we saw this. Like this is one of the requirement. There should be no loops. So we can avoid this by having directed acyclic graph. First one is true. A choice state can make a transition to any state in any machine. So this is wrong. Like it can make transition within the same machine, not to any machine in the ham. So this option is wrong. Stop states terminates the episode. So was this the role of the stop state? No, it wasn't. So stop state basically returns the control to the machine which called it. So this is again wrong. And action states emit primitive actions. Again, this is also true. So these are like simple facts about HAMS. Like if you have watched the lectures about HAMS, like you would know these options easily. Okay, so I think like some voice is coming. Maybe I'll mute you. Okay, so now I'll move to the next one. So is hierarchy of the abstract machine the core in hierarchy of the abstract machine? Okay, this is concerning about HAM. The core MDP state changes only when we visit a choice state. Does it happen when we visit a choice state or like it used to happen when we visit an action state, right? So again, like this is false. So if there is any doubt, you can ask me. Otherwise, like I'll move to the next question. We'll wait. Okay, so I'll move to the next question. So the next question is again a true and false. So this says that flight optimal policies are always, so this always is the keyword here, always easier to learn than our recursively optimal policies. So suppose maybe I'll give you an example. Basically, like these flight optimal policies are typically harder than the recursively optimal policies. Suppose if we consider an application where like there are 10 states, suppose. So, and binary actions. Binary actions means like zero or one type of action. And like we also consider like a deterministic policies. So in this scenario, like this flat optimal policies will search in a space of 2 raised to power 10. Two, like in each of the state, like there are two possible actions. So this will be the policy space for flat optimal policy corresponding to S. But if we have like we have divided it into sub problems in this recursively optimal policy, and like we try to find the optimal policy corresponding to each of those sub problems. Suppose we have divided these state, we applied state abstraction and divided it like 2, 3, and 5. Like two features of two states in one of the abstraction, three in one another, and five in another. So we will search in policy space of 2 raised to power 2 plus 2 raised to power 3 plus 2 raised to power 5. Like in this we will search one policy, in this we will search another, in this we will search another. So this is like a significantly large number, right? So in this way, like we can, by the simple example, we can demonstrate that flat optimal policies are not like there might be cases where flat optimal policies are harder to learn than recursively optimal policies. And in fact, like this happens most of the times. So typically, like it's harder to learn flat optimal policies than recursively optimal policies. And also, like if like it was easier to learn flat optimal policies, then we would have focused on them only. Like why would have we have introduced these recursively optimal policies in the first place? Okay, so if there is no doubt, I'll move to the next question. So again, like this section got over. So the next section is problem solving. In this, like I'll be discussing questions which are not part of practice assignment or assignments. So first question says that suppose that in solving a problem, we make use of state abstraction. So state abstraction is basically like we allocate some features to each of the subproblem. We make use of state abstraction in identifying solutions to some of the subproblems. Okay. In this approach, is it possible to obtain a recursively optimal solution to the original problem? Yeah, like it's possible. You can like find the optimal solution in each of these subproblems, and just you need to have a way of combining them all. So you can have a recursively optimal solution to the original problem. And like generally, like this is not so if an abstraction is called a safe abstraction if like the recursively optimal solution and the like flat optimal solution are equivalent. So then we call that abstraction is a safe abstraction. And if we do like feature selection in like a very careful manner, so that like only the features which are required for solving that subproblems are part of that subproblems, no extra features and no less features also. Then in that way, like mostly like we will end up in recursively optimal solutions, which are actually the solutions to the original problem. So it is actually possible. So the answer is yes. So if there is any doubt in this, you can ask me. Otherwise, I'll move to the next question. Okay, then I'll move to the next question. So second question says that what kind of solution would you expect to obtain if in solving a problem, policies for each individual subproblem are learned in isolation? So this is simply like the definition of recursively optimal solution, right? So because we are learning them in isolation. And in this, we in hierarchical optimal solution, we respect the hierarchy, but we don't learn in isolation. We learn like in a together manner. Like you remember that example in which like we didn't that room example in which like there were two gates, suppose here, and maybe like the optimal policy in recursively optimal policy could be different. Like for here, like it would be to come here and then go there and somewhere like here. Similarly, so this example we have already done in class, but as you saw in that example that the hierarchical optimal solution considered the entire thing because like then like if we were in some place here, then if the goal state was here, then we would actually move here instead of moving to this nearest gate, which would have been the case in recursively optimal solution. And flat optimal solution, again, like this is like not even considering hierarchy. So you cannot say like this is also wrong. So the correct answer is recursively optimal solution. Again, most of these questions this week are theoretical questions because like it was mostly theory in the lectures also. So do the policies of individual options need to be defined over the entire state space of the MDP of the original problem? Like were we defining options on the entire state space? Like the main reason why we use options is like we have some component which we can reuse, right? And if like this component is expanding over the entire state space, then what's even the point? So we do not define over the entire state space. Generally, like there is some state space where we have an option in this region. And then for another region, we could have another option. Like you remember that example, suppose building to main gate. Like you can have one option here, one policy which is getting followed here. So in that way, like we do not need to define the option over the entire state space. So again, this is no. So the next question says, consider the two-room example discussed in the lecture. Okay, so this is from the lectures itself. And suppose you define two options. There are two options, O1. So O1 option like takes the agent in room 1 to room 2. So we had that left room, and this is the goal state. So option O1 like takes the agent from this room, left room, to the right room. I'll call it 1 and 2. And this is option O2. And what does option O2 do? It takes the agent in the room 2 to the goal state. Okay, so once we are in O2, like this room 2, like we will go, this option will take us to the this goal state. So assuming that you have appropriately specified the initiation states, initiation sets and termination conditions for both the options and are trying to learn the individual option policies. Okay. So here the key thing is like we are trying to learn the individual option policies, not the entire policy, not the overall policy, right? Just the individual option policy. So O1 will be applicable in this room and O2 will be applicable in this room. And we are learning the policy for O1 and O2. Would you need to use SMDP queue learning or conventional queue learning will suffice? Like in this case, like conventional queue learning will suffice, right? Because in this case we want to learn a policy like O1 will learn a policy how like how fast we can get from room 1 to room 2. So it can learn by simple queue learning itself. Like SMDP queue learning will come into the picture when like these options also overlap with primitive actions. But since here options are like one after the other, so once this gets executed, then only like second will start. It's not like O1 is like calling O2 or O2 is calling O1. So in this case, like conventional queue learning suffices because like we are learning the individual option policies. If there is any doubt in this, you can ask me. Maybe I'll check once. Okay, so there's nothing. I'll move to the next question then. So next question says, consider Markov policy. So Markov policy over options. Markov policy basically means like only the current state is sufficient. We don't need information about history. So over options. So like this is policy and it's a stochastic policy because it's using a probability distribution. And now like this is a policy which is a mapping of from S, like this is the set of states into set of options to 0 and 1. So this is the policy over options, where S is the set of states and O is the set of options. Assume that all options are Markov. So this is also one of the assumption that all the options are Markov. So any action will depend only the current state within that option. And while the policy mu selects options by considering the primitive actions being selected in those options, we can determine another policy pi. So there is another policy pi which is corresponding to mu, but is a conventional policy over action. So pi you can define like S cross A to 0, 1. So this is a conventional kind of policy. So, but the question they are asking is like in general, will pi also be a Markov policy? So remember like this thing, we cannot write just the current state here because in this policy pi, like it is like corresponding to this mu. So it is taking actions which are within this option, like within the option specified with this mu. So basically like we need some information about which option we are in. And that information will come from history, like when this option started. So some kind of history dependence is there, right? So this we cannot say like it can be represented in this form. So it won't be a Markov policy. Like it is like in this case, it can be a non-Markov policy also. So the answer is it can be a non-Markov also because it has to be a non-Markov because like we need to know like which option we are in and that option might have started like sometime in the past, right? So you need current state, just the current state won't suffice. Like there might be some more states in between. and you need to know like when this option started. That will basically give you information of which option you are in. So this historical dependence basically like makes it non-markov. So now I'll move to the next question. So this question says that consider the following problem design. You have a grid world with several rooms as discussed in the lecture. Okay. With the goal state in corner cell of one of the rooms. So the same problem. You set up an agent with options for exiting each of the rooms into the other. Okay. So options are defined like for exiting each of the room into the other. So in this problem, like there can be like more than two rooms. Okay. Can be. But you have defined an option for exiting each of the room into the other. So all possible combinations of options are there. Now you also allow the agent to pick from the four primitive actions. So the four primitive actions basically like left, right, up, and down. So those are the primitive actions. And there is a step reward of -1. So this step reward of -1 basically means that the agent should try to go to the goal state as soon as possible. So the learning algorithm used is SMDP Q learning. Okay, so they have used SMDP Q learning and with normal Q learning updates for the primitive actions. Okay. For primitive actions, we can make the normal Q learning updates. For options, we will need SMDP Q learning. So basically, in general, it's SMDP Q learning. And you expect the agent to learn faster due to presence of options. So this is something which you expected to happen, but discovered that this is not the case. So in fact, like it is actually slower. So they are asking, can you explain what might have caused this? So basically, like by introducing options, the learning process became slow. So what could be the reason of this? So first option says that the options are not useful for solving the problem, hence the slowdown. So again, like this is false. Options like these options are actually useful. Like they will define how to exit each room into the other. So they are actually helpful. Once we are in one room, we can like actually go to another room based on these options. So they are helpful. This is not the reason. So initially the agent will focus more on using primitive actions causing slowdown. So what this means is suppose you are in some state and there might be some gate to go to another row. But in between, like there are some steps which you need to take. So if you take a primitive action, you are getting a reward of -1, just -1, because it's one step. But you have the possibility of using an option here. But maybe it's suppose 1, 2, 3, 4, 5 step. So an option will give you a reward of -5. Like this is considering like that gamma is equals to 1. Discount factor is 1 here. So either way, like with -1 reward, we can have gamma equal to 1. We have already seen this in few of examples before. So in this initial phase, like what will happen, like this agent has two options, whether to take a primitive action and get a reward of -1, or whether to go for an option and get a reward of -5. So initial phase, initially like this agent will prefer this one because it's giving higher reward. Higher in the sense like -1 is greater than -5. So this is like extremely negative. So agent initially won't prefer to go for options, but eventually like when it learns, it will go for options also. But this initial phase like basically causes the slowdown. So this is true. Now, due to the presence of options, we can no longer achieve the optimal solution. Hence, this takes longer. Again, this is false. Like presence of options is actually helpful. And it takes longer because we are using SMDP Q learning compared to conventional Q learning, which is faster. Like we cannot say that. Like sometimes options make things fast because like we like remember that example in which we were going from building to main gate. So if you had an option which like basically tells like how to go in the fastest way from building to main gate. So in that case, like it will actually speed up compared to conventional Q learning. So again, this is also one. So if there is any doubt, you can ask me. Otherwise, I'll move to the next question. So the next question says it's about intra-option Q learning. So in intra-option learning techniques, we can learn options even without ever executing them. Is it true or false? It's true, right? Like if we have like suppose many options, so 1 or 2 or 3 or 4. So remember we saw an update where like suppose if we are executing option O5, but like this option O5, suppose it's consistent with option O1, then we can update option O1 also using this option O5. So it's possible to do that. You can learn about options even without ever executing them. So O1, like we never execute them. There is an option O5, like we execute that option, and on the basis of that, we can make updates to this option O1 also. Now we'll move to the next question, which is the last question of this section. So suppose that you have identified a set of subtasks for solving a large problem using hierarchical learning approach. Okay. To solve each subtask efficiently, you want to constrain the primitive actions that can be executed within each subtask. Right. So like remember that example, like suppose you are going from building to main gate. Like you need only actions like walking or running or maybe like cycling kind of options. But once you are on the from main gate to you are on highway maybe, then you'll need actions like go on bus or something else, like book a cab or something, right? So like these actions like can be constrained. So in like some tasks you won't require some other actions. In some other tasks, subtask, you might require some other actions. So you want to constrain those primitive actions. So the primitive actions will set will actually comprise all of these actions, like union of all those actions. But in order to constrain that, in some subtask, you take only those actions which are relevant there. You want to constrain that. So the question is specifying such constraints is possible in options. Can we do that in options? Suppose options is following our policy, suppose PI. So in that PIO, we allow only mapping to actions which are constrained, like which are actually helpful in that subtask. So we can constrain there, like maybe in some option O2, like if the poly this is O1, pi O2. If O1 corresponds to this phase, you can allow actions like cycling or walking or running here or jogging. And if option O2 corresponds to this one, you can allow actions like take a bus or take a cab or something like that. So you can constrain in option also. So options definitely you can constrain. Now let's see if we can do that in HAMS also. So HAMS like like basically like we will have a machine. Like there might be machine and this machines will have we can simply like these machines are finite state automata, right? Finite state machines. So you can limit the action states like each of these machines will have some action states, right? Action states. So you can simply limit the action states within those machines. Like you can like suppose this machine corresponds to this one, you can allow action states like walking, jogging, or running, or cycling kind of. And if you are in this one, then you can allow actions like take a bus, take a cab, all those kind of actions. So you can constrain in like options also, hence also. So again, like this would have been like you can do in both. So basically, like the correct answer is both because like it's a single option correct. Either way, like don't write this. Like this is the C is the correct answer. So with this, like we have come to the end of problem solving session. Now I'll move to demo. So before that, like if you have any doubt in any of the questions from the previous two sections, you can ask me now. And today's demo will be on like first demo is on policy gradient. Like this is basically vanilla policy gradient. And second demo is on active. This is also like vanilla. Vanilla means like plain kind of like basic version, not without any advancements. So as we will see later, like there are many variants like DDPG, and many sophisticated algorithms which came up from this policy gradient. And there is advantage actor critic, and there is asynchronous advantage critic, soft actor critic. So all those advanced kind of algorithms are there. Like I'll provide you references to them either way, but like the demo like today will concern policy gradient and active critic only. And like this I am doing in this session because like last time like we planned to do DQN and policy gradient, but we couldn't do it due to lack of time. So I'm covering it in this one. Okay, then I'll share my screen. Maybe someone can confirm, like if you are able to see the browser. Yeah, okay, fine.
Yes, sir. Visible, sir. Thank you, sir.
Okay, okay, yeah, got it. So again, like for both these things, like we will be both these like policy gradient also, active gradient also, we will be considering the same environment, card pool, and you might be familiar with this environment. Action space is discrete, like whether to go left or right. Observation space, which is basically the state space, like there are four variables like card position, card velocity, pole angle, and pole angular velocity, and like these are their like minimum values and maximum values. And the reward is basically +1 for each step. So the goal is to like not let this pole fall down. So if this pole falls down, then the episode will terminate. And even if like if you go left or right, like to the of the screen, then also the episode terminates. Also, like there's a time limit also to truncate this episode. If like it's in the middle, then 500 is the time limit. So only 500 time steps are allowed. So maximum limit is 500 time steps. So this is the same environment which we will be using for both these demos. So again, like this code, like policy gradient, I have taken from reinforcement, deep reinforcement learning in action book. And again, like these are the simple imports. So as usual, like we will be using PyTorch in this demo also. You could have gone for TensorFlow also if you want, but I have a preference for PyTorch, so I'll go with PyTorch. So these are the imports: NumPy, Torch, Gym, Matplotlib, and warnings. So maybe I'll open the Gym one. So again, like this is a utility function to calculate the running mean. So basically, you might remember one of the demo in which like we didn't average out, then like entire graph got filled with red color because like there were so many episodes to point that we couldn't figure like fill that efficiently. So again, like here also we will be calculating a running mean. So that same function is there, and environment is card pool version 0. So this is the same environment. Now like this is the policy network. So policy network is defined using this torch and basically like we have a sequential neural network. I'll show you like what this neural network looks like. Okay, so we have like input layer. Input layer, there will be four nodes. Because like we have four state features. Remember those velocity and position and angular velocity, four features of the cardboard. And then in the second layer, we have how many nodes? L2 is 150 nodes. Number of hidden layer nodes is 150. So there will be a hidden layer like which is like 150 nodes. Suppose 150 nodes are there. There are four nodes and input layer. And finally, like we have two actions, right? So we will have two actions. So this is the like number of nodes in output layer. So this is how we define. So basically, like there will be connections between them. So you can make those connections. Uh, all those connections will be there. So this is like connected network, and this is our policy network. So two output nodes. So basically, like you will pass a state here, and it will return like values corresponding to these actions. So basically, like here, like we will be using softmax. So softmax, what it does is like softmax, you might remember from softmax policy. So suppose if it gives some five value here, three value here. So we convert this to probability kind of thing. So it will be e raised to 5 upon e raised to 5 plus e raised to 3, e raised to 3. And for second one, it will be similar, but e raised to power 3 upon this same denominator. So this will like kind of convert into a probability, and whoever like has a higher probability, then we will take that action. Like it's not like we are doing like deterministic policy. So we will be following a stochastic policy. So if like suppose probability of this comes out to be 80% and this 20%, so we will generate a random number between 0 and 1. If it comes out to be less than 0.8, then we will take this action, otherwise we will take second action. So this is a stochastic policy, not a deterministic policy. You can have a deterministic policy also in the way that if like whatever action has the higher probability, you always take that action. So that is also a possibility, but here like we will be using stochastic policy. So the advantage of using stochastic policy is that you don't have to explicitly do exploration. So this stochastic policy will implicitly do the exploration for you. So you don't need those action greedy kind of things. So I hope like you are able to get this. So now I'll move to the, so this is how like you define a neural network in PyTorch. So this is a sequential. Sequential basically means like one layer after the other. And so first is a linear layer, like which has weights like 4 into 150 weights will be there. So this represents that. And the activation function in this is leaky ReLU. So you might remember ReLU activation function from last lecture. So ReLU is like this. So suppose this is 0. So for negative portion, it's like here 0. But for here, like it's like linear. So this is ReLU. But what happens in leaky ReLU is this. So you can get from the name of itself, like it's kind of leaking something. So it's leaking, but the slope is not that much as this one. So maybe like it's like if it's like y equal to x here, then you can have like y equal to 0.1 x here, that kind of. So some leakage is here on the negative side. So that is leaky ReLU. So this is the activation function of this layer. So all the like neurons of like hidden layer like will have leaky ReLU function, activation function. Now like this, there is another linear layer which is L2 L3. So it will be 150 into 2 weights. So 300 weights. If you have biases, then you will have plus 2 here. And if you had biases here, so 4 into 150 plus 150 biases corresponding to each neuron. And in the like final layer, we have this softmax. So softmax, I have already mentioned like how we calculate that softmax probability. So this will basically assign probability to both the actions. So here like our actions are two, but if it would have been more actions, then also softmax works. So learning rate, this is alpha, like which is the update. You remember those update equations in which like we will make the updates to parameters of the policy. So there is this alpha, and this is the learning rate which we are using 0.009. And again, like the optimizer is Adam with this learning rate. I mean, like this is like a simple test, like how we are going to do all these calls. So first we will like this, you remember environment reset function. So this simply returns the start state. So this we generally call at the beginning of the episode so that we get a start state to begin with. Now, once we get a start state, we can call this model because this model will take that state and give like our probabilities as the output. So we will have that like prediction of the model will come from this model. We have simply passed the state, and this is like basically converting it to a tensor format. So we are calling the policy network model to produce the predicted action probabilities. Now, once we have those predicted action probabilities, our job is to like sample an action. So remember I mentioned that we are using a stochastic policy, not a deterministic policy. If it was deterministic policy, then you could have simply used argmax to select the action whichever has the highest probability. And if like there is a tie, then you could have a uniform tie breaking criteria. And otherwise, like we are going with stochastic policy. So basically, on the basis of those probabilities which are written to us here, like we will sample from that probability distribution and get like whatever action is written to us, we will take that action. So this thing is happening in this step, sample an action from the probability distribution provided by the policy network. And once you have the action, now you have the state, you have the action. Now you can take the action in the environment and the environment will return to you next state, which is the state two reward. And then you remember like whether the episode is truncated or terminated. And info is a dictionary we won't be using here. So again, like this is the again and another function like you remember in policy gradient methods we need to have discounted returns. So all those rewards will come here. And with this gamma 0.99, like we will be discounting them and calculating the returns basically here. And also like one thing to notice that we are normalizing the rewards in 0 to 1 interval. This is simply to improve the numerical stability. So max normalization is there. So we are dividing all the values by whatever max is there. And again, like you remember, like we had this loss function. So there, like in theory, like we were performing gradient ascent, right? So we didn't have this minus sign, but here, like we are performing gradient descent because these PyTorch and all like they are written for considering gradient descent. So we put a minus so that it becomes ascent essentially. So this sum you might remember return into log probability. So log, like basically log of pi, like this is not the gradient one. So that term like gradient is not there. Once we take the gradient of this one, then we will get the term which was discussed in the class. So this is the loss function as of now. Like as of now, like we haven't taken this gradient because PyTorch is calculating that gradient for us. So we don't go there. We simply mention the loss function to it. Again, like maximum duration of an episode. So within an episode also, like we are setting this limit to 200. You can set it to maybe like you remember like either way like 500 is the maximum limit, maximum number of time steps within an episode. So this is the time limit within an episode. How many time steps? We have like set it to 200 because like just like to have like mm, run this like in a short amount of time. And the maximum episodes we have set it to 500. Again, like you can play with this later, like you can set it to 1000 episodes, maybe see if it improves learning. And gamma is the discount factor 0.99. So this gamma will get passed here either way, like its default value is also 0.99. If you don't pass, it will take 0.99. And score is the list to keep track of episode length over 20 times. Remember, like in this case, like the reward will essentially be equal to the episode length because each time step we are getting a reward of +1. So we can track the episode length also. So that can serve as the score of the how good the performance it is. And this is the actual training loop. So here, like for episode in range of max episodes. So this loop is over the episodes itself. So 500 episodes we have. So for those 500 episodes, what we are doing is we are getting the like basically the start state here. So by this reset function and initially done is false. And this is transition array like basically to transition list to store the transition state actions and rewards. And for T in range max duration, like remember we defined this as 200. So within each episode, we will take maximum of 200. And if like at some point before 200 it gets done, we will break out of this. So again, within this loop now, since we had the start state, we had the start state, we can like pass that start state to the like model and model will return the action probabilities. This we have already seen those 4 lines of code here. So same lines here. So once we have the action probabilities, we can get the like we can sample the action according to that probability distribution. So we are selecting an action stochasticity. And once we have the action stochastically, then we will like this is simply like making the we are having a previous state variable. So generally like people use next state, but here they have used previous state. So previous state becomes the current state and they are storing the next state in the current state. So this kind of conversion you can do. You could have used like next state and current state also, like it wouldn't have mattered. But like remember, like those change will like this line will come later if you use next state. So here like you are getting the next state. Reward we are not considering because like reward either way we can calculate because reward is essentially the length of the episode. So which this T is kind of doing it. So we don't need reward, so we don't store it. We simply use underscore to keep that reward. Done, we will need it here and info again dictionary we want to use it. So and once we have this transition, we are storing it. And now we have stored this transition, also checking like if the episode is done. If it's done, like then we break out of this loop and move to the next episode. And now here, like we are doing that calculations of losses and all. So for each episode, remember like in policy gradient, we do updates at the end of the episode. So because we are using returns. So this is episode length is the length of the transitions, how many transitions we have stored, and score is like, remember we defined this score array, score list. So we are appending in that score list the episode length. So this basically serves as a score of each episode, and this we will be using for plotting purpose only. And reward batch, like again, like this, we are sampling from this transition. So we have this transition list of storing transitions. From that, like we are getting the batch of reward batch. Then we have already defined this discounted reward function, right? So this will basically calculate the return on the basis of these rewards which we send it to this function. And once we have the discounted returns, this discounted returns will actually serve as our targets in the loss function. And we have the state batch also, action batch also. So what now we also need to have the predictions of the model, right? We have the targets, but we need to know our own prediction. So here, like we will pass this state batch to the model and get the predictions out of it. And then that prediction batch, like we will take probability corresponding to only that action that was actually taken. And once we have those, then we can calculate the loss easily. Like this is our target, this is our predictions. So this is the loss, and loss function we have already defined above. And again, like zero grad is basically to clear out any resident gradients. So like when this loop is getting executed, like there might be some gradients of the previous episode. So in order to make that zero, like this zero grad is called, and backward basically calculates the gradients. So remember in loss function, we mentioned just the loss function. We didn't calculate the gradient. So that is happening here automatically for us by PyTorch. And this will basically make the update. So remember that update equation. So update the parameters of the policy, and our parameters here will be these weights, right? 4 into 150. If there are bias, then plus 150. So all those parameters are there. Those will get updated in this optimizer.stat function. So this is essentially the training loop, entire training loop. So once we have the training loop, now we already have this score array. We have stored the score. So now we plot it like how it looks like. And remember, like I mentioned that we use this running mean function so that like this entire graph is not filled. So in order to have a good idea like how things are happening, we use running mean of 50 windows and 50 size window basically. So basically that running mean will be like last 50 episodes, whatever is the average that will get plotted. And this is basically plotting. So also you remember episode duration can be a good proxy for the reward because in each in each time step within that episode, like we were getting a reward of +1. So this is the like training episodes. Also, like remember, like this here, like we are not using discounting. Although, like in reality, since we have discount parameter as something which is not equal to one, there will be discounting. But either way, like we are ignoring that discounting for every of the episode, so it doesn't matter much. We can use simple score sum, and this is the plot. So basically, you can see like with episodes, like the average reward which we are getting is kind of improving. Basically, the episode duration is improving, and in the end, like we reach near 200. And remember, like we said, the maximum duration is 200. So 200 was something which we wanted to reach, and we actually reached 200. And so this is the like training graph. What happened in the training? Now we want to evaluate it. So we evaluate it using 100 different games and see like how the results come. So this is the evaluation phase. So here, like again, same thing is happening. We are starting with a start state with this environment reset, and we are doing for 100 games. So for 100 games, we are doing this prediction from the model and taking action according to that, like by choice. And basically, like this is sampling according to that probability distribution written by this model, and then we are taking that action and getting the next state reward and all those, and then we are changing the next state to like current state to next state, and also t plus equal to 1. And if like at any point if we have reached 200, then we will break it. And again, like at the end like of this episode, we reset it, then equals to false, and we are appending this in this score array, score list. So again, like converting to numpy and plotting a scatter plot. Now you can see here, right? like this is purely evaluation. So once like this was at the end of the training. So at the end of the training, we have reached a model which was giving this kind of reward. Now we are evaluating on this model, like a fully trained model. So once we are doing evaluations, you can see like for most of the episodes, it's almost giving 200, which is like something which we wanted to achieve, right? So some episodes like it's giving maybe like something bad happens and there like the reward is not 200, but most of the episodes you can see like the reward is 200. So if there is any doubt in this, you can ask me now. Otherwise, like I'll go to this further experiments. So what you can do is you can try with different hyperparameters. Remember, like in NN architecture, I simply like use the 150 hidden layer neurons. You can use something else also. Like this number need not be 150. Although like input and output, you cannot do much about it because like there are four inputs and the two outputs, two actions and four like state features. But what you can do is you can add one more layer here. Like you can use two layer of like maybe 15 to 50 neurons. You can use three layers also. Here, like only one layer was used of 150 neurons. You can use single layer also with different number of neurons because this is simply a hyperparameter. We know like I simply said it like you can use something different also. So you can play around with that and that actually like affects the performance. And again, like you can try out like deterministic policy also by taking arguments instead of stochastic policy. And also you can play around with this. You remember like there like we were using leaky ReLU. Here, leaky ReLU, you can try different activation functions, see what happens with just ReLU. Here, obviously, you will need softmax, but you can try out different activation functions here also. Like you can play around, like you can have different layers also, more than one layer. So all those experiments you can try out and learning rate, like again, like we set it to 0.0009. You can try out different learning rates and then number of episodes you can increase. Although like this is good performance, not bad, but you can see like if you are able to achieve good performance with like less number of episodes by simply modifying the other hyperparameters. So that kind of things you can do. You can change the max length of episodes. So I set it to 200. You can set it to 250, 300, or even 100 play out with different max length of episodes and you can obviously play around with discount factor and set it to 0.999. You can set it to like whatever you want, one, even one, or like 0.5, whatever, like you can try out and see like what happens with this discount factor. And again, like cardpool is just one of the environment. So you can try out different environments also.
Sir,
Yeah.
excuse me, sir.
Yeah, yeah.
Sir, that how to relate that gradients. The gradient means we used to say that that future parameters are in steps. It is being optimally being tried to converge in small steps or long steps kind of things. We used to think that way now. So gradient convergence
Right.
kind of things.
So that is like those step sizes coming through this learning rate. So learning rate affects the step size. So you can like change this learning rate, make it large. So larger steps will be there. Otherwise, if you want small steps, then you can have small learning rate.
Okay, that is being taken care by the PyTorch kind of stuff algorithm or something. What's up? Is it so, sir?
Here, like we are not using research kind of thing. So we are simply using learning rate as a proxy for it. So you can set those step length using this learning rate itself. So this will like kind of have an impact on this. You can try out different learning rates and see like whether the speed improves. Like sometimes what happens, like we might actually overshoot the like maybe I'll explain here. So suppose this is the like our policy loss function, right? Loss. So this is the global minima. These are like local minima.
Local minimum. Okay, sir.
So
Okay.
sometimes what happens, like suppose if you are taking a larger step, then suppose you
Yes,
are
sir.
here, you
Yes,
might
sir.
actually miss this, and suppose you are here, you might actually miss this. So you have to
Yes, sir.
like balance that carefully. So that is like handled using learning rate. You don't want it to be too small also, otherwise
Too,
it will take a
too
long time
bigger.
to get there. And you don't want
Yes.
it too large also so that you skip. And sometimes those
Exactly.
oscillations also happen. So those kind of things you want to avoid. So you need to have it optimal, and that is actually embodied using learning rate.
Got it, sir. Thank you, sir.
So this is the first demo. So again, I'll be sharing this with you.
Sir, apart from this, can I have one question regarding that pick and place kind of can throwing some rover kind of thing, which is being discussed in our oral book now, sir, in early chapters. Pick and place kind of can throwing the can into the trash
Ah,
can kind of.
right, right. So as of now,
Yeah.
I haven't read that problem, but maybe you can post something on discussion and I'll see.
Okay, sir. Thank you. Just I'm asking whether you would have come across or if you would have
No,
seen
no,
anything
not
kind of.
yet, not yet.
Okay, sir. So that because it is being discussed in our book, and sometimes someone might have tried or something like that. That's why
Mhm.
I just asked for your idea. Thank you very much. It's okay,
Right,
sir.
right.
Thank you, sir.
Okay. So again, this is the second demo. So these are the inputs. So this is active critic one. So here, you remember in policy gradient, we simply use the returns as the R. Where is that equation? This is the loss function. So this is just the return. But here in active critic, we will be subtracting a baseline from it, and that baseline will be actually our value function. So instead of R, there will be something like R minus value function. So that is also known as advantage. So these are simple imports, torch, matplotlib, and the numpy gem. Again, this is a tuple for saving. So again, like the same environment with same observation space. So remember, here, we won't need just a policy network. We will need a value network also. So what will happen here is, this is the first layer. So first layer, either way, you'll have four inputs for both the network. And here, they have used 128 neurons in the second hidden layer, basically. So four inputs. And here, it's 128. Right? This is policy network. Right? And value network, again, four and 128 in hidden layer. Now what happens here is this. Now for action head, basically the policy network, the number of outputs will be two because we are using two actions. We are having two actions there. So we want softmax probabilities corresponding to two actions. This will be policy network. But in value network, we simply pass the state and we want just one value, right? So we will have just one node and it will output a real value. Real value. So here, a softmax, due to softmax, it will output probabilities. So here, this is happening. So you can see here, affine is there. So 4 into 128, this affine is common to both of them. In this forward function, you can see. And in this affine layer, we are actually having value function. So both of these, in this layer, hidden layer, we are having value activation function. And then what happens? Action probabilities are gotten by this softmax. So we are having this action head. So 128 into 2, these weights are there for corresponding to policy network. And you take that action head and then take softmax. So this is the policy network. And otherwise, you take the value head. Value head is basically 128 into 1. So this is the this network. Just a minute. So second network, so there will be 128 into 1, this number of weights. If you are not having biases, otherwise, if you are biased, then you will have one more bias variable here. And then what happens is, in this, you don't really need any activation function, right? In value function, because we simply want to output a real value, and that linear will simply do that. You don't want to put anything extra on top of that. So linear will output a real value. So no extra activation function in the last layer for value function. And this is basically returning the forward will return the outputs of both the policy network also the value network. So this way, these two networks have been defined, and you can see using PyTorch, how elegantly you can write within and so less number of lines you can elegantly write those two networks. And even in training, you saw just by optimizer dot zero grad, then backward, and then step. that is sufficient to do the entire update process. Now, again, like this is the function to select the action stochastically. Like same thing is happening, like which I mentioned here. So what happens, suppose if action A1 is with 0.75 probability and action A2 is 0.25 probability. So what you do is you draw a random number between 0 and 1. And if it happens to be less than equal to 0.75, you take action A1, otherwise you take action A2. So this is basically like the thing which is happening in this function. Like although when I it's using something else like categorical and all. So those are coming from here. But either way, like the basic thing happening there is this. And the only thing to note is that we are using a stochastic policy. We are actually sampling, not taking arguments and taking the best action. You can actually try out that suppose if action even has a higher probability, then you can take that action deterministically. So you can have that deterministic policy also, but again, you will need to ensure that you do sufficient exploration. So that exploration for exploration purpose, we are using this stochastic policy. So here, like we are having a function to calculate the actor and critic loss and perform back propagation also. So this is simply a definition of a function. We will be calling it later. So the definition is basically we are getting this saved actions from the model itself. So model like we have defined later. Either way, like this is just a function definition. So by the time we call this function, like it's called quite later here, finish episode. So by that time model will already be defined here. So it doesn't matter much. And this finish episode is basically getting the saved actions from the model. Remember, like in this model itself, like there are these variables, initialized variables like affine, action head, value head, and also saved actions and rewards. So these two variables are also stored. So in this function, like we are also having like policy losses, like list for storing policy losses so that like we can calculate the overall one and value losses also and returns also for storing. And what we are like in this loop is simply doing is calculating the return. Now, again, like there we were doing max normalization. Here you can do standard normalization. This epsilon basically ensures sometimes the standard deviation might be very close to zero. So this epsilon ensures that we don't do division by zero. So this is also defined here. So either way, like this is just the definition, so we can define it before. And when it gets called, it will take this epsilon. So it's a small value to avoid division by zero in standard normalization. And also like for this, like we are calculating for each of this, like remember this tuple we defined. So this from this tuple, what we are doing is for log project saved actions, comma returns, we are calculating the advantage. I remember I mentioned this instead of just the return, we are like using return minus some baseline, and this baseline in actor critic is simply the value. So this value is coming here, and this is the policy loss which we are appending. So negative of log probability into advantage, and this advantage is R minus value. And like remember in like vanilla policy gradient, it was simply R, not the this subtraction of baseline. So this is happening here. And the value losses, for value losses, it's a real number kind of thing. So you could have used even L2 loss, but here they are using smooth L1 loss. So you can use that. You can actually try out with L2 loss what happens. So L1 loss is generally like sometimes it's not differentiable at some points, like those corner points. So there are these points like L and L1 loss suppose. So at these like beaks, like it's not differentiable, so it's made smooth so that it becomes differentiable. So this is like smooth L1 loss, and then again like resetting the gradients to zero if there are some resident gradients. And here like loss we will stack up like because we want to do both of them together. So it will either way get passed to different networks, so that's not an issue. So this is the stack of both these losses, policy losses and value losses. And then we are like actually taking the backward step, which will calculate the gradients, and then step will basically make the update. So this is simply a function definition. This we will call it later. And again, like we are deleting these rewards and saved actions for new episodes. So this will be called every episode. Now here, like they have actually defined an instance of this policy class. So we define this policy class here. So one instance of that class is created, then optimizer, which is getting used is Adam. And learning rate here is 3 raised to power minus 10, 3 into 10 raised to power minus 2. So again, like this is one of the hyperparameter simply used because it was there. You can play around with this and see like whether the convergence speed improves or sometimes result get worse also. So all those like caveats are there. You need to try out them yourself. And this is epsilon, which I mentioned just to avoid division by zero. So this is the main training function here. So again, like here, they are also using running kind of reward. And for I episodes, so 500 episodes are there. Again, like the same thing, getting the start state, episode reward is set to 0. And for D, like this is simple collection of data. So select action, like remember the select action will basically where is this select action? So when you pass this state to the select action function, it will basically call the model first. And on the basis of model, like it will get those probabilities. And on the basis of those probabilities, it will sample one of the action and then return that action. So this is happening in the select action function. Either way, like here, it was just the definition. So it will have access to model, like because either way, it's getting called after model is defined. So here, like where were we? So again, like once you have the action from this function, then you can take the action in the environment and get the next state reward and this done variable. And you can append this rewards and increase the episode reward by this whatever reward you got. Either way, like in cardpool problem, it's just one, but in other there like this setup is general. You can use it for other problems also. So here, like they have used this reward variable, and if like you are done, the episode is terminated, you can break. Then again, like here, like they are using running kind of reward. So basically, like they are not changing it drastically. So some 0.05 contribution is coming from the episode reward, and some like old like 95% contribution is still coming from the old running reward. Now here, like we are actually calling this finish episode function. So this is getting called and it will basically like make the update, calculate the losses and perform back propagation and make the updates to the parameters. So this will happen for each episode and these are like simply for printing. So you are printing the last reward and the average reward. So this is actual reward which you are getting and this is the like this running reward. So we see like both of them and in the end like if you reach a certain uh, desired level of reward, then you terminate. That you say that you have solved this cardboard problem, and that is again set in this environment to be 200. So that's why like that is one of the reason why we took max number of episodes in like our previous demo also has 200 because 200 is generally considered a decent performance. So once you reach 200, like you can say that your implementation is good. So here, like this train function is again, it was a function only, so it's getting called here. And you can see like as we like increase the episodes, our reward is also getting increased. And eventually, like after like 220 episodes, like remember, like we have a check also, like we are breaking out of this loop if we have reached sufficient performance. Otherwise, like it would have run for 500 episodes. But within like 260 episodes only, we have like five consecutive, like 50 consecutive episodes where like we are having 200 rewards. So we are kind of converged. So we are breaking out of this loop. So this is the episode reward. This is also the learning, like running reward kind of thing. And this also like gets close to 194. And all this like took around 47 seconds to execute. Now, like this is the training part. Now we actually want to evaluate this. So remember, like this network has actually converged to like 200, like for like this many episodes, it was giving 200. So it's a very good performance either way. And like now we will see like this function is simply for evaluation. So we are having this sports array as before. And here like we are simply counting the number of steps because that is essentially our reward also. So it is a proxy of the reward because either way discounting will be applied to all the episodes itself. So we can kind of ignore it and see as a proxy like what is this. And again, same kind of thing, like you are getting an initial state, then until it's not done, you are calling the select action module, and this will return the action to take the action in the environment and get these rewards, and append keep on appending these scores for every episodes. And I mean, like when we plot this, like you can see like in policy gradient, it was like some of the episodes were actually below 200, right? But here, like you can see, like the convergence is almost perfect. So most of the episodes is 200 word. Most, not just most, but in fact all. But there might be issues, like there might be overfitting also, but you can try out with different hyperparameters and see like if like this same result is getting there. And also remember, like this whole implementation is stochastic because we are using stochastic policy. So maybe on one it's like this, on some other one it might happen to be something different. It might be below 200. So you basically like do maybe 30 runs or something and take the average out of it. So generally in stochastic setting, like we do this 30 runs and then 30 or more, whatever number of runs you want to do, and you take the average performance. So that will be our evaluation performance. Here, like just one is there. So you can run this notebook like multiple times and see like what is the average and how many runs you are actually getting optimal performance. So this is like just a demo. So again, like what you can do is hyperparameter tuning is one thing, different environments. So again, beyond this cardboard, like there are many environments in this. So maybe I'll show you. Gym. So see, like there are Atari environments, Mojoko environments. There are a lot of environments. These are slightly complex ones, but you can play around with this classic control key. So in classic controls, you have Acrobot, this card pull is there, mountain card. In this, like you have to get the card to the this flag. Pendulum, and again another mounting card, like this is continuous version, this might be discrete version. So you can try out with different classical environments. Again, if you are interested, you can go to like continuous action problems also. So like in this, like in our toy example of this one, cardboard. Like there were only four input features, but maybe in these games, like state features will be much larger than four. In Atari, in fact, like the entire screen will come as the feature. So if it's like 1020, like maybe not 1024, maybe 32 into 32, then 1024 notes will be there in the input states. So all those things are there, and sometimes you need to take continuous actions also. Like in our case, cardboard, like there were only left and right action. But in some of these games, you might have to actually specify like by which velocity you have to move and all those. Like in this game, suppose you need to move left and right, but by how much also. So there is some continuous kind of thing here. So you can try out these environments also. Also, last thing which I would mention is you can try out other algorithms also. So I have mentioned like vanilla policy gradient. Maybe what we discussed this vanilla policy gradient and vanilla actor critic. By default, if actor critic is mentioned, then it's referring to vanilla only. I think there is something in chat. Okay. So nothing is so what I have done here is like in the reading section, I have inserted some links. So I'm showing those links. I'm opening one of them. So this is one link. And again, like this spinning up DRL, I have already mentioned to you before. So like there are a lot of algorithms like advantage actor critic, then asynchronous advantage actor critic, and most of these have come after these lectures were recorded. So you can explore them if you want. Although like these won't be part of your exams, but if you are interested in learning them, you can try out this. And there is soft actor critic, then trust vision policy optimization. Similarly, like there are different variants of policy method optimization methods also, like proximal policy optimization, then deterministic policy gradient, then there is deep deterministic. So this will actually use neural network. And there is before PG also distributed kind of thing. Then there is multi-agent also, then twin delayed. So all these algorithms are there. So what I have done is like in the reading section, I have inserted these two links. So some popular algorithms you will either ways. So here in OpenAI spinning up also you can find so much of their focus is on policy optimization also, like key concepts in RL, like this will be like you will already be knowing all these concepts, right? Terminology, states, observation, what is policy, deterministic policy, stochastic policy, like basic like definition kind of things, trajectory, reward, return, what is other problem, value function, on policy, off policy, all those kind of things. Optimal Q function, Bellman equation. So that is like something, this is advantage function, which I was talking about. So advantage function is basically like this Q function minus V pi of this. Remember like the return which we were using was a proxy for this one. So minus some baseline and some more formalism is there. So this is like the basics. So this you can do it easily. But after this, like they have discussed kind of RL algorithm. So this is like the taxonomy. So basically, like we have discussed policy gradient, basic policy gradient, deep Q network, and I think that's it. So most of the algorithms basically like you have to cover it on yourself. So also like I think we haven't touched this model-based RL itself. So in model-based RL also there are a lot of interesting algorithms. Like there is one called uh we are right here. DynaQ, and fitted queue iteration is also a like model-based algorithm. So this we have done one at least. And in model free, like we have done this queue learning, then it goes to deep QN, and we have done this policy gradient. But after this, like there are a lot of algorithms. This so you can try out all these algorithms. C51, QRDPN. This is hindsight experience replay. So we had that experience replay. There are different versions of experience replay also. One is prioritized experience replay. So PER, so you can try out those. So here like you'll find details about model free versus model based, like and what to learn in model free. So most of them like you will have like concepts you will know, but which algorithm is in which setting, you need to know that. And what does that algorithm do? So here like they have provided all the links to these algorithms also. Like this will basically direct you to the paper itself. So you can download the PDF from here. So, but sometimes what happens like you don't want to read the paper itself. So for that purpose, we will have these blocks. So here, like in third part, like they have actually focused a lot on policy optimization itself. So policy optimization is like very important nowadays. So people have a lot of focus on policy algorithm, policy-based approaches. So you can see here like deriving the simplest policy gradient. This we have already seen in class also, like all these steps. So this is the summary of this. Like remember that reward, but this is the gradient. So without gradient, it will basically become log probability predictions and this return. Then baseline subtraction and all those things. So you can see about this, how to make the loss function. All those details are here. And even like they have some code snippets and everything here. So there's like so this will basically cover you like these algorithms. Vanilla policy gradient we have already discussed. You can see trust region policy optimization, proximal policy optimization, TDPD, and then this TD3. So this is not TD kind of temporal difference. So there like TD lambda is between 0 and 1. So TD3 means twin delayed deep deterministic policy gradient and soft activity. So all these algorithms are there. You can learn some of them from this one. And second block which I have referred is this policy gradient algorithm. So this is like a quite popular blog. You like it will take you some time to read. And if you are reading for like first time, then it will take you even more time than that. So here like they have discussed the notations and all. Usually like the notation is consistent with what we have used. So you can see policy gradient and policy gradient theorem, like it was discussed in lectures also. Proof of policy gradient also we have seen theorem. And then like then one by one, like this will blog will introduce you to all these algorithms. So reinforce we have already seen. Reinforce, then actor critic like baseline subtraction and off policy policy gradient. And then there is A3C, which is asynchronous advantage vector critic. Then A2C. A2C is basically synchronous version of A3C. So then deterministic policy gradient, DPG. You can find some details about this. Then you can like find links to paper also code if there is available. So you can find implementations of these algorithms and either in stable baselines or even like some of the blocks will provide you. So deterministic, then there is deep deterministic. This will actually use neural networks. And then D4PG, which is distributed distributional DDPG, and then multi-agent. So till now, like whatever applications we saw is single agent based, right? There is one RL agent and which is basically trying to maximize its own expected reward. There are settings where there are multiple agents, and this is actually the more realistic setting. Like it's not like just one robot and the environment. There could be multiple robots and an environment. And it won't be like one player playing chess. There is a rival also. You can model that as an agent also. So two player. So like all those multi-agent frameworks are also there. So this corresponds to multi-agent DDPG. Then there is this trust region policy optimization, and different variants are there. Proximal policy optimization, and this PPG. Like this is not that popular. Maybe like if you want, you can read it. Acer also not that popular. And all these like soft tech that we take, you can read. And other variants are also there. So basically like TD3, like twin delayed, deep deterministic also is there. If you like basically like this won't be all these Impala is there. All these like won't be part of your exams, but if you are interested, like you can continue learning after your exams also. So this is like where like you can go if you want to pursue further. And all these references are also there. This is our book also, and all these papers. So you can like this is a regress block. Like you can like bookmark it and save it. Like you can keep on coming back to this block again and again. So I think that was it for the demo part. So if there is any doubt, you can ask me now, like in either of the demo. Otherwise, like I'll move to the last section, which is the assignment. Also, what I wanted to tell you is this thing. Like, see, there are different kinds of reinforcement learning also. See, like you have done RL, you are doing hierarchical reinforcement learning, and there is DRL, which is deep reinforcement learning. And apart from this, there is inverse reinforcement learning, there is multi-agent reinforcement learning, multi-objective reinforcement learning. So in this, like there are multiple agents, right? Here, like inverse thing happens. You actually run the reward function, not like the thing will we do in our multi-agent. Like there will be multi-agent, multi-objective. So like generally, like we have one objective function, but there could be two objective function that minimize maybe time and maximize maybe goals scored, something like this. So conflicting kind of objectives could be there or even cooperative objectives. So all that comes in multi-objective reinforcement learning. So different kind of reinforcement learnings are also there. So if you are interested, you can like someone asked in last lecture, like what could be the potential research directions. So you can like after RL, you can pick one of these and see like what's happening there. And then there is usual Monte Carlo tree search and all. Variants are there, then alpha, rho. So you can read up all those kind of algorithms, model based. So most of these are like examples of decision time planning, these two. So you don't plan like for what happens is like generally in RL, what happens, you will plan like you'll have a policy which will say like if you are in some state, what is the action you will take. But generally like this you will pre-plan and store it as some policy, maybe as a neural network or as a tabular approach. And then when you see that state again, you refer to that neural network and see like what action it gives. But sometimes what happens is you have time to compute. Suppose you are playing the game of chess, you have reached some state, you get like some time, 5 seconds something, suppose. So within that 5 seconds, you can run some algorithm, like three kind of search. Like if I take this move, then this will happen later. This might happen, and if you have take this move, then this might happen. So on the basis of that, you can calculate like what is the optimal move in this state. So all this planning is happening at decision time. We don't care like what would have happened if some other state would have been here. We only care about if we have reached that state. Once we are in state, from that state we do planning, and then we move to the next state. Then again, like we do planning from that state. So these are like decision time planning algorithms. So like these are the basic areas where you can look. And also like a lot of research is also going on in like how to, like you might have heard of this Occam's razor. So this basically means if two models are there, M1 and M2, both are giving same performance, but M1 is less complex, like less number of parameters than this M2, then you go for M1. So basically we go for model like which is less complex if like both are giving the same performance. And sometimes even like if the performance difference is not that much, then also we prefer, even if it's less, we will go for M1 because simple models are basically like don't overfit. So this kind of concepts are also there. So very now what is happening like in deep RL, like uh, till now like we have seen simple neural networks, but there could be like we have used only feed forward neural networks, right? Feed forward neural networks. There are those RNNs, LSTMs network. So all those like type different types of networks, transformers are coming up in RL. So basically like these consume a lot of computation time, also computation resources also. So how to make RL efficient, work efficiently. So that is also like one of the goal. So that is also one of the research area. So different research areas are there. Maybe like if you want to know like what are the popular research areas, then you can like maybe search in popular conferences like NeurIPS and all. So there are popular conferences ICLR, ICML, and there is NeurIPS. So you can search in these conferences and maybe add a tag of reinforcement learning and see like what are the popular topics currently. And also like this, I have mentioned about full RL, but in bandits also like there is a lot of research going on in bandits. So this is like evergreen kind of field. So bandits we covered like in initial few lectures. So in bandits also like there is a lot of research. So with that, I think like I'll move to back to the slides. So maybe you can confirm if you're able to see the slides now, right?
Yes, sir. Yes, sir.
Okay, okay. So maybe like with that, I'll move to the assignment. This is assignment 10. So question number 1. Consider the update equation for SMDP Q learning. So this is the update equation which is giving to us QSA is equals to QSA plus alpha times A and plus B times max of action Q S dash A dash. Okay, so max is over A dash, so it doesn't matter minus the whole S. So this is the usual Q learning equation, but the point they are asking is like for SMDP Q learning, what will be the values of A and B? And RK is the reward received at time step. K gamma is the response. So was it just RT and gamma? This would have made it conventional Q learning, right? So this is not. And this is what is this? RT plus gamma times RT plus 1 plus gamma times is tau minus 1 RT plus tau and V is equals to gamma tau. So basically like there was this time delay, holding time. So which was tau. So if you factor in that, you will see like that which of these options is the correct one. This is the correct one, right? And here what's the issue? Like you don't multiply by gamma t in the beginning itself, right? You discount it after that. This is wrong. Also, this is simply gamma t, not one step kind of thing. So this is also one. So if you have like watched the lecture only, like you would have got this easily. Now the question two says consider an SMDP in which the next state and the reward only depend on the previous state and action. Okay, so basically this means that next state and reward are like this. So this is the like joint distribution. You can write it as product of individual distribution. So here like what's happening this joint. So basically they are saying next state and this time like is kind of independent. So next state and reward only depend on the previous state and action. So also like in traditional, like in SMDP, you will have this kind of thing. So here they are saying that this is independent of tau, no dependence on tau and reward also, and no dependence on tau of this next state also. So this joint distribution can be written as product of these two. So that is the thing because like this next state is depending just on S and A. It's not depending on tau. So that means like it's independent of tau. Then you can. This is basically conditional independence. Given S and A, like this next state and tau are independent of each other. Now, if we solve the above SMTP with conventional Q learning, we will end up with the same policy as solving it with SMDP Q learning. So they are saying is like if we use conventional Q learning instead of SMDPQ learning? Like, will we like both of them will end up on the same policy or no? So still like one thing is missing. Like you remember like delay, there will be a delay. So due to this delay tau, like there is some more discounting that happened. Remember that equation in last slide, this one. So this extra factor of delay gamma tau comes right in our update equation here. And here like it since that delay is there, then it will be like this. These many rewards, accumulated rewards. So due to that, we cannot say that it will converge to the same policy, right? So let's see the options. First is yes, because now tau won't change anything and we end up with same states and action sequences. I mean, like yes is definitely wrong. So no, okay, with no we have two options. So again, you can discard this one also. Yes, because the Bellman equation is saying for both methods in the case. So also you might remember that sir also asked you guys to like read the paper and find out the Bellman equation. So there is a paper, recent advances in hierarchical reinforcement learning. So I have linked that paper in the readings section. So you can read it from there, like the Bellman equations. So, like the answer is definitely no, but you, since this is the assignment, I won't give you the exact answer. So you need to figure out it's no, but because of what reason? Is it this reason because the next state will still depend on tau? Here they have clearly mentioned that the next state and the reward only depend on previous state and action. So why will it depend on tau? Here, like they have already mentioned, next state will depend only on previous state and action. Here we can see also next state is depending on state and action only, not on tau. That's why we can break this joint distribution into this product of distribution. So again, this is also. So with that, you can get the answer. So now I'll move to next question. So this is concerning HAMS. So in HAM, what will be the immediate rewards received between two choice states? So there is a finite state machine, and in that, like there are two choice states. So what will be the immediate rewards between them? So in choice state, like we might go to some lower machine, we can call like with this choice state, you can go to some other state and then go to some call other machine. And in like at some lower level, there might be primitive actions, but you can take like a lot of primitive actions in between. Suppose if this top level machine was like maybe go to station. So this might call initially like go to main gate. And here like the actions, primitive actions could be like maybe take right, then take left, all those kind of actions. So there could be many actions, right, in between. So since there are many actions, so what will be the immediate rewards between two choice states? So in between two choices, say there could be multiple primitive actions. So will it be the return of the next choice state? The reward of only the next primitive action taking. So will it be just if you are in a room, just go outside the room? Will it be something like this? No. Like it will be kind of accumulation of all these, right? And third option says immediate reward is always zero. This is also no. Immediate reward can be not need not be zero always, right? So it's basically an accumulation of immediate rewards of the core MDP obtained between those two choice points. So there could be two choice points, and they're like whatever like things you saw in between primitive actions. You need to accumulate the rewards, and if there is discounting, you can do discounting. Otherwise, just a simple sum. So I hope like there is no doubt in this. So now I'll move to the next question. So this is like multi-option, correct? So which of the following is true about Markov and semi-Markov options? So in a Markov options, the options policy depends only on the current state. It is true, right? And in a semi-Markov options, the options policy can depend only on the current state. It can happen, right? So generally what happens is, like if you see like this is the Markov option, in which like you are depending only on the current state, right? And this is the semi-Markov, in which you are depending not just on the current state, but you can depend on previous states also. But there might be a case where like semi-Markov and Markov are equivalent. Like you have an option to depend on history, but you need not revoke it like you need not do it every time. So there could be a semi-Markov option where the options policy can only depend on the current state. This is also possible. So basically, like the thing is like every Markov option is a semi-Markov option also. So this happens due to that. And in a semi-Markov options, like the keywords here are can and may. They are not saying always, right? So if it was always, then this would have been wrong, right? So in a semi-Markov options, the options policy may depend on history since the execution of the option. Again, like this is also true. And last option says a semi-Markov option is always a Markov option, but not vice versa. So they are saying semi-Markov option is always a Markov option. So this you can figure out from the diagram. And on the basis of that, you can get the answer. Is it like semi-Markov option is always a Markov option? Or is it Markov option is always a semi-Markov option? So on the basis of that, you can figure out the last option and get the answer. So now I'll move to the next question. There is no doubt. So consider two statements for an SMDP for a ham. So, okay, so basically you need to tell like which of them are true. So the state of the SMDP is defined by the state of the base MDP, SI maybe, call stack CI, and the state of the machine currently executing. So you might remember this, right? There was a Cartesian product of these entities. Like this MI came later, but either way, like you'll take Cartesian product with that also. And this will be the state of the SMDP. So this is true. But the question is second, so this is true. So you can like rule out these two options. The actions of the SMDP can only be defined by the action states. So like this you need to see like the actions of the SMDP can only be defined by the action states, or like was it something else? Like did like so mentioned when defining the action space of SMDP, was it like just the action states or was it like the states which you can transition from a choice state? So like is that equivalent to this thing? Like on the basis of that you can get the answer. So it was like whatever states can transition on choice. and you can like take the union of all those. So like, is this like other like action states? Suppose you take union of these action states and the states you can transition from the choice state. If these two are equivalent, then you will say true. If these two are not, then you will say this is false. So that you can figure out. So, the sixth, this is again a multi-option correct. So which of the following are possible advantages of formulating a given problem as hierarchy of subproblems? So this is basically asking what are the advantages of hierarchical reinforcement learning. So reduce state space. Is this like one of the feature? Like yeah, you remember? Like otherwise, like if it wasn't reducing the state space, then why would we have bothered to do it? Remember, like what happens like if you are like this is main gate, suppose here you don't need feature state features which are like corresponding to highway, like traffic and all. Once you are like inside this main gate, you need those features once you are outside, right? So all those features will become relevant outside. So this will essentially, otherwise, like it would have been simply one vector of like all these features, right? Like so, it could have been like maybe like if each feature can take maybe three value, then you could have if this length is 1, 2, 3, 4, 5, 6, 7, 8, 9. So you could have 3 raised to power 9 states. But since like you divide it, like maybe only these first three features are relevant inside, then you will search in like this will be your possible state space. And maybe next six features. Like, so this number like will be lesser than 3 raised to power 9. So in this way, like we have a reduced state space. I think there is something in check. Maybe I'll see. I think it's some other check. So more meaningful state abstraction. So state abstraction is basically like hiding out features which are not required. So if we divide into two sub problems, like one is going to main gate and then go main gate to station maybe. So you don't need features here, like which are relevant here in this portion. So that is essentially state abstraction, which leads to reduced state space also. So more meaningful state abstraction. This is an advantage of hierarchical reinforcement learning. Temporal abstraction of behavior, is it possible? So yeah, like there is temporal abstraction of behavior also because like remember that factor tau, like which was basically hold out time. So holding time. So like you take an action and then there was dot 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 some time and then that action is actually. So there might be some things happening in the environment. Maybe like some your action might have actually changed the environment. So in order to settle those things, like you have this delay. So there is temporal abstraction of behaviors also. So this is also true. Like basically these three are the advantages of uh, using HRL. But is the last one also an option? Is the last one also an advantage of HRL? So reusability of learned subproblem. So this like you can figure out on yourself. Like if you have learned a problem subproblem optimally, then you can reuse it again and again. And you might remember like this is actually like one of the reasons why we introduced HRL in first place, so that we can reuse. Suppose you have learned walking perfectly, then you can use walking in maybe many problems like going to station or going to classroom. Many there could be many problems, but once a problem will be walking and that you have already optimized that you can do. So now the question is, so if there is any doubt, you can ask me. Otherwise, I'll start with this one. Maybe I'll check this. Okay then. So in SMDP, consider the case where tau is fixed for all state action pairs. Okay, so this tau, like in class, it was discussed that tau is a random variable, but like here they have mentioned that it's fixed, like same constant value for all state action pairs. So will we get always the same policy for conventional Q learning and SMDP Q learning then? If like tau is fixed. fixed number. Please provide answer for the three cases when tau equals to 3, 2, or 1. So remember that question which we saw slightly earlier. I was also asking about this one. Like this conventional Q learning and SMDP Q learning, will they end up with the same policy? So the reason there was like no, because like tau will still depends on state action pairs, and like here, like we have assumed in that question that it won't depend, it's a fixed value, but discounting may also have an effect on the final policies, right? So remember, like those gamma, if you have like tau equals to 3, then something like gamma cube will appear. If you have tau equals to 2, then something like gamma square will appear in that equation, which we saw earlier, A and B, right? This is concerning just the B factor. So there like gamma 3 can appear, gamma cube can appear. But if you have tau equals to 1, then just gamma will appear. Then this will reduce to conventional cube, right? So in the case of tau equals to 1, you can say yes, it will reduce to, like both will give the same policy. And even like you can see there also, like if you see here, this equation. So here like gamma cube will be there, then gamma square will be there for second one, and then last one it will be just gamma. So it will reduce to Q learning equation. And let's see A. So if gamma is like the tau is just one step, right? So it will be just this factor, RT plus gamma times RT, right? So you can have that also. So it's just one step, so it will be RT only because this bootstrapping is happening already here. So it will be just RT. So in that way, you can see that only RT will appear. Otherwise, if it was like tau equals to 2, then these two terms will appear. Otherwise, like it would, there would be tau equals to 3, there will be one more term, gamma square, RT plus 1. Right? There is gamma tau minus 1. So for 3, it will be till gamma square. So due to this discounting, you cannot say like it will be same for tau equals to 3 and tau equals to 2. But for tau equals to 1, it will be 3. So on the basis of that, you can figure out the answer. So now the question is 8, true and false. So in the classical options framework, each option has a non-zero probability of terminating in any state of the environment. So remember that probability beta. And at any point, it was mentioned that beta can has to be non-zero. It can be zero, right? There can be terminal states in which you can simply terminate in some state with definite, like there could be states which are essentially terminal. Suppose in a game of chess, like if you are in a checkmate state, that has to be terminal. You need to restart again. You cannot say that it's, and there will be probability like of 1, you can terminate with that. So here they are asking each option has a non-zero probability. So there could be states like where you can have zero probability of terminating also. Like maybe like in this game of chess itself, like suppose consider the start state itself, like where all the pieces are like just there. So you cannot like in just one move, you cannot simply checkmate the king and all those things. So you cannot, there you will have zero probability of terminating. So again, like this is false. Might happen, but not always. So there are actually states which will have zero probability. So with that, I'll move to the ninth question. So suppose that we model a robot in our room as an SMDP. A robot is in a room, such that the position of the robot in the room is the state of the SMDP. Okay, so whatever like coordinates of the robot in the room is there, like it's the state of the SMDP. Maybe if you are using XY, just maybe it's walking in 2D plane only, like it's not jumping robot. So just XY coordinates are sufficient. Which of the following scenarios satisfy the assumption that next state and transition time are independent of each other given the current state and action? So again, like this equation we have already seen before, like this is the conditional independence. So basically like given state and action, like this next state and time taken is kind of independent of each other. So assume that primitive actions are left, right, up, down, and it takes a single time step to execute. Okay. So this is the important thing. It takes a single time step to execute any of these actions. So the question which they have asked is like which of the following scenarios, there are like few scenarios, will satisfy this assumption, like this condition. So if the room has a single door and the actions available are exit the room and move left, right, up, down, then obviously like this is kind of independent. Like if you have given the state and the action which you have taken, suppose this is a big room, you are in this state and maybe I'll draw gray. Suppose you are in this position and you go left. If you are given this information that you are in this state as and you have taken left action, and on the basis of that, that is sufficient to calculate the time. Suppose exit is here. That is sufficient to calculate this, like the time, right? You don't need you don't have any dependency on next state. On the basis of, in fact, these two information, you can deterministically calculate the next step itself and the next state itself, and also the like time from this state, because since you know the action taken also and this state also. So here, like you can say, like this, these are independent. But if the room has two doors, now this is another exit, right? So if you are in some state, so your exit will actually depend on like your next state. So suppose there might be possibility that if you go there, if you are targeting some exit, like this will basically mean like how much time you are taking to exit the room. But this will actually depend on which exit you are planning to take. And this will, suppose if you are moving towards this exit, then it might be different, right? So you cannot say this, that in that case there will be some kind of dependence, right? This is all. So, but if the room has two doors and the options are just move left, right, up or down, there is no like exit action. So basically this means that you are staying within the room itself. So like basically in the second case there might be situations then this exit the room action might create those different kind of delays, because exit the room, like there might be one room, one door, kind of like maybe small kind of door in which like maybe you can take just 2 seconds, and another door could be like it has a big lock kind of thing and you need to remove this lock first and then go out, maybe backup kind of door. So that time might be different, so which exit you choose like will kind of decide this time. So next state dependency might be there. So here, like, but there is no option, no action of exiting the room. Just you are staying inside because left, right, up, down. Okay. So the room has two rooms. So in that case, like you can say this independence can be there. Now, if there is no doubt, I'll move to the next question, which is essentially the last question. So, okay. So which of the following is the correct Bellman equation for an SMDP? So basically, like this was asked to you as homework. Either way, like you can read it from the paper itself. Note that our SA is this is the reward is a function of only SA and S dash. So they are asking of optimal value function, not like just the value function of a policy pi. If it was value function, then there would have been summation over action. So this max is fine in all the four options. Now you see like what we used to do in value function. In value function, it used to be, remember like what is the like summation over next states, and there used to be a reward plus 10 gamma times and some value puts the. But see like this option, what it's doing, uh it's not summing up over sigma over next states. So that thing is missing. This is wrong. Then what is the issue with this one? So it's summing over S dash and tau. And but this probability distribution is wrong, right? It should be probability of S dash tau given SA. tau cannot be like next state cannot depend on tau. So again, like this is wrong. So here, like it seems good, sigma over s dash and tau. And yeah, like because we are doing this, these are the like two possible options, and we are summing over them. Then reward, like and the gamma times. Also, there will be this tau factor also. And so this is gamma raised to power tau, not gamma into tau. And we start as this. So this seems legit, right? So if you read the paper, you'll find that this is the correct option. And the last option is what is the issue with this one? Again, like the tau is missing, right? So this is also wrong. Either way, like I have linked that paper also. So these are the like reading materials. So till now, like we were following Sutton and Bartow, but what happens now? This HRL thing is not there in Sutton and Bartow, but like those guys have contributed in this reinforcement learning. So like these are the papers. Like this is recent advances in hierarchical reinforcement learning. So you can read the first four sections. If you have time, you can read like even further sections also. But you should try to read first four sections because this is kind of replacement of your book. So this is the survey paper which was getting talked in the lectures. And like this survey paper is generally well written than the original papers. Like this was the options paper and this is the ham paper. So if you want to go for ham and options original paper, so you can go there. But this paper, like survey paper, like kind of summarizes both of these in a very nice manner. So maybe it's better you can go for this. So you can read this. And also, like I mentioned that I linked some, like this is the blog like which had uh, information about different policy gradient algorithms and spinning up in DRL, like this is the usual one. And also like there are two more blocks which I'll discuss briefly. Like, just a second. So I'll share the screen. Okay, so this is the blog, and this is another blog. So this is like quite famous blog, Pong from Pixels. This will actually explain you like mainly DQN and stuff, like how the that Atari game thing came up. So this is like a game of Pong, like where you have to prevent this ball from going to the background, left or right. So please have to move. So this like how this raw pixels came up and probability of moving up was model. All those details are in this blog. And this is like a very relevant blog. You can read this. Like this is from Andre Karpathy, I think. So it was although it was written in 2016, but still relevant. So you can read this blog. And this will basically introduce you to deep Q networks and deep Q learning. Also deep reinforcement learning, which started from there. Also, like I have linked another like this is kind of free type of course, like blog kind of thing. So you can like if you have time, you can keep on reading this also. Introduction to deep reinforcement learning, then deep reinforcement learning with Huggy. So this is on Hugging Face and all those like Q learning. This you already know. So deep Q learning with Atari games, then remember, like in most of the demos, I mentioned that hyperparameter tuning you can do it manually, but there is a tool for doing that Optuna. So you can do that also policy gradient with PyTorch. So good thing is like they are using PyTorch here, so it would be easy for you to adapt. And introduction to Unity, ML agents, then active critic methods, and multi-agents also. This I mentioned that till now, like we are focused on just single agent, but there is a multi-agent RL also. And then you can see these proximal policy optimization, and this Doom is a game. So you can see that how it's applied there. And some more advanced topics in reinforcement learning, like model-based reinforcement learning, like offline and online reinforcement learning, then generalized facial reinforcement learning, then RLHF. This you might have heard in. This was used in ChatGPT. So you can learn about this also, RLHF and decision transformation transformers and offline RL. So all those like different curriculum learning is there and Unreal Learning Agents, Root RL. So some of these like even I haven't heard the name, but you can read about them if you want. These are relatively new. So language models in RL. So all those things are there. So this link is also there in the um, reading material. So okay, so these are the like this is the course link and this is the form from pixels and spinning up and policy gradient algorithms. So these are the links and with that like I'll end this session. So thank you everyone.
Thank you very much, sir. Great session, sir. Thanks a
Yeah,
lot,
right.
sir.
Okay, welcome. Okay, so then I'll stop sharing. Now I'll stop the recording.